Next week, I'll be spending as much time on the assignment as necessary, just like this week. Any questions, please send them to me by mail, or in person, ask them in person in class. Both is okay with me. And I hope you'll do much better. Today, the theme is scientific revolution, and one of the questions in the assignment is also about the applicability of the term scientific revolution. As you may have noticed, the term is not used, the phrase is not used in the syllabus. I think you can write history without mentioning the phrase scientific revolution, at least the history of mathematical practices you can do without mentioning the term. But it is a very common phrase anyway, so we should at least see why it is used. And this used because it is part of a standard view of history. A history wherein there are dark ages, and mind you, dark means gloomy and, intellectually not very taxing ages. The kind of ages where people were better off when they could wield an axe, as if they, and not so good off when they were good in their mathematics. So the dark ages, very dark ages. Then comes in Copernicus, showing that, hey, it's not the Earth, or it's not the Sun orbiting the Earth, it's the Earth orbiting the Sun. Our solar system is different than we supposed to until now. Then comes in Galileo, who emphasizes that even more and produces pictures of the Sun and the Moon, which are not perfectly spherical, who talks about laws of nature, which are kind of appalling to many at the time, because laws are put forward by God or a king, not by nature. And Kepler, showing that the planetary orbits are not exactly circular but slightly elliptic. Descartes, many others, and then true science was there. That's the standard story. So from then on, science marched onwards. Go Galileo to the right, saying, I have done my observations correctly. That's the true scientific way of investigating. Contra the church, here in the form of a Jesuit priest, who opposes this whole idea and thinks that we should return to the Dark Ages. That's the kind of picture that's standard. I'm going to debunk that picture for you, not because I think it's entirely untrue. I will leave some room for this more romantic picture here, but because there are things to be said about it, and things to be said that make the scientific revolution both less scientific and less revolutionary. And that's, I think, worth mentioning. And we know it already. We've seen Carol of Aurillac last week, and we've seen Alfonso the Wise last week. We know that there were, in these dark ages, people who were very much in favor of doing mathematics. So, where does this picture of these dark ages come from? Were they that stupid, these people? No, definitely not. Well, there were other job requirements at the time, indeed. So they were not striving for the perfect mathematical knowledge that we today hold for perfect mathematical knowledge. But they were doing and they were favoring mathematics. And in the syllabus there are many other examples. Nicole Oren, Thomas Aquinas, monks, people in the monasteries who were digging into mathematical knowledge and adding to that even. Creating new mathematical knowledge in the Dark Ages. So, if you want to spot mathematics before, say, 1500, you don't go looking for mathematics books, although there were some rare examples, they were there, but you don't go looking for that. No, you go and seek out theology. Books on theology often contain mathematics. In theology were the brightest minds of Western Europe at the time.
Theology.
Theology, yes. That's where the people wanted to go and study. That was the main. So that's how you became Pope, or how you could become Emperor. That's by studying theology. And in law. But law had its own sense, its own way of going about with numbers. Lawyers are much more, well, how do you say, blunt-minded, but yeah, this is prejudice, of course. But in theology were the brightest minds of Europe. And there, in theological treatises, you will find arithmetic and new things being discovered. There you'll find Nicole Oram writing about the congruence of the geometrical series, for example. Things like really awful or really wonderful stuff that you really can imagine, really can admire as mathematics. But it was regarded as part of theology, partly because they spoke of infinitely many numbers to be added, such thing. But yeah, that's where you can find it. So it was there. Here it is on paper, printed, early 15th century. The Margarita Philosophica, the Pearls of Philosophy. And in the Pearls of Philosophy, you'll find the quadrivium, so the four mathematical subjects, being arithmetic, music, geometry, and astronomy. That were the four mathematical. And next to this quadrivium, there was, of course, the trivium, the three subjects that are today called trivial. Yeah, that's all three in language: rhetoric, grammar, and dialectics. So these are the trivial matters, and the quadrivium, that's the higher part of philosophy. And in this Margarita Philosophica, in this textbook for Freiburg students at the time, but it was soon disseminated to other universities as well, you may find more than just these four mathematical subjects. More subjects were added to mathematical treatises. Most notably, the construction of sundials, so measuring time, making use of the sun to measure time, but also making use of the sun to construct a calendar and to calculate the day of Easter. These kind of things were part of mathematics, and valuable parts of mathematics. You can imagine it's very valuable for a monk to be able to calculate the day of Easter. Yeah. And for many, constructing a new calendar is quite heavy work. Several calendar reforms have been taking place in the course of centuries, most of them in the late Middle Ages. So, there was a lot of mathematics going on before the scientific revolution. You just have to know where to look for it. Yeah, okay. And, mind you, it had a peculiar status. You see on the title page of this book, angels. The angels with their wings, they protect and make sure that the knowledge that you find in this book is actually at the last pages where there are beautiful pictures. And notice that there's a lot of text and not that many numbers in it, but it's all about arithmetic. And the second one, that's from 1478. The second one is a little later, a few years later, 1483, if I'm not mistaken. And it's a printed one, that's the manuscript. It's a printed one, and it's a German arithmetic on modern numbers. Modern numbers. Practical work. These people were thinking of bookkeeping, of surveying, of blogging. That kind of practical hands job, standing with your boots in the dirt, or at the desk writing and doing the practical jobs that were required for life, for the economy, for their livelihood. The picture, by the way, fits, of course, the use of mathematics as they saw it in medicine. This is an early 17th century picture where the doctor shows us the working of the blood streams in the body. So it's circular blood stream. That's what he illustrates by what he proves, you could say. He thinks that it's a mathematical proof, at least he calls it a mathematical proof, that the blood stream is indeed circular by showing off one or two veins and then seeing that that they redirect and then make a new blood stream run. But there were those two worlds of mathematics. In the syllabus, I try to emphasize that by from chapter 2 onwards, describing them two different sections of the chapter. There was the Latin world of university at court, and those were mostly monks, mind you. Here you see Luca Pacioli, in a painting, of course. Yeah, and the painting to his right is the Duke of Milan, who was paying him to do his work. And in the painting, he is showing off his mathematical knowledge. It's not just Euclid that he knows, what he does on the slate and what he's, it's the construction of a Dolic Adico, the one on the right there, on the book. But to his left, there's dangling from the ceiling a non-regular solid, a Archimedean solid, which is semi-regular. So all the lines are equal, but not all the faces are the same. So you have this one has squares and regular triangles. So it's a almost regular polyhedron. He's showing off his mathematical, and he is a monk. It was, mathematics was practiced at the universities, was practiced by priests. Those were the people who could show off with this knowledge. Those were the people who were close to court. And this other world of mathematics was the more mundane world of surveyors, of robbers, of fortress builders, of bookkeepers, of bankers. That people who wrote the books that are handed around here in the classroom. I'll have some more books handed around in a second. Yeah, here is a picture of the French engineer Dow. He in his epigraph you may read toutes choses par raison de mesure et à briser de nature. So if you reason about everything by numbers, by measure, then you'll be able to describe nature. That's kind of what he that was his life. And he designed fortresses, as you may see. The kind of fortresses that were needed to keep out the guns of the enemy. Yeah, you may recall that if you have come across old medieval walled city, then Avignon, for example, if you ever go to Avignon, you can still see that. These walls are simply put up high and are not very broad, but they are walls. And to keep them aloft, you need a tower at every 50 meters or so, yeah, or a wall built flat by itself. But towers, walls, high. That was the idea of a medieval walled city. That way you could keep out the enemy. But with the invention of the cannon, you can imagine, it's very easy from a large distance to shoot one of these walls and simply have it pulled down, and you can march in with your army and devastate the rest of the city. That was the fun way of going about in that day and age. To prevent that from happening, these kind of fortresses were constructed to lay out points filled with earth, so walls, but then filled with earth, so you can shoot a gun at it, but the earth will kind of, both the ricochet, because you have an unfortunate angle where you're pointing your gun at, but also the earth will catch a lot of the force of the cannonball reaching the wall. So you won't breach the wall that exists. That's the idea, that you have these kind of wall cities all around Europe. Still, the most common one here in the vicinity is Naarden. Naarden and still has this layout visible in its city plans. So take the train and marvel. So these two worlds of mathematics were there. The Latin world of Universitas and the mundane world of simple mathematics. Which of these two worlds revolutionized, or did they revolt perhaps? What was it that really changed? Well, here, and I can't stress that enough, is the Jesuit College of Oxford. Jesuit, all these colleges, all these colleges, Oxford, Paris, anywhere in the world, were universities we would call today. Yeah, these were church people working there. They were monks. Yes, yeah, they were church people. Was Galileo as well? No, Galileo was one of these odd ones out that I described in the book as, yeah, the in-between Universitas and the lay people, the bookkeepers and the surveyors, the one who could work at the court. There were not that many courts, so there were not that many positions as court mathematicians, you can imagine, but they were valued. Yeah, you could get a job as a mathematician at the court. So it paid off to do mathematics. Yeah, you wanted to get there, even if you were not that great in your language skills, you could get a position at the court. So what was really changing there? Well, Copernicus, for example, Galileo was the other one. Copernicus, he was one of these monks. Why did he think of that insane system where the sun was in the center of our solar system? Very, very, very easily. Because that, to him, saved the idea of describing the solar system in terms of circles, and circles alone. Yeah. The movement of the planets from the point of view of the Earth is quite intricate. And because you spot them from a turning sphere, you see them moving forward and forward. And that was helped by, or that was described by cycles, epicycles, epicycles, and even more epicycles. Every time that measurement of the planet movement became more accurate, more epicycles were needed to save the system as described, to build good predictions of the positions of planets, to have a good system. Yeah. So, yeah, it can't have been that. God can't have made it that complicated. Let's turn things around. Does it work when I conjecture that, just suppose that the sun's in the center and that all the planets do move around and the Earth is somewhere between the other planets in Mars? And hell, it works. It makes things a lot easier. Does it help in computing? No, it doesn't, because you need to go and construct new tables, which takes a lifetime's effort. And so until the late 18th century, or until the late 17th century, most people still, for convenience's sake, in all calculations, used the geocentric tables, because they were available. But the heliocentric tables being constructed by the end of the 17th century and become printed by the end of the 17th century were, kind of the obvious big out. So he tried to give a better description of creation. God must have been smart. He can't have made it so difficult for us to describe the stars and the movements of the planets. That was Copernicus' idea. And so was Galileo's. What did they get into? Where did this idea come from? Well, several things happened in the 15th, 16th, early 17th century. And one of them, and I'm going to go across these four things, one of them was the inventing of the printing press. And this, of course, affected the dissemination of knowledge. You can imagine. Here's a popular and very romantic picture of Johannes Gutenberg, who, according to the Germans, invented the printing press. practically every country in Europe has its own hero who has invented the printing press. Well, we have Koster. In France they have someone as well. In Germany they have Gutenberg. And I must confess Gutenberg hasn't passed answer, but in several places the printing press was imported from China probably, where it was having known, the process had been known for decades already. And was used here to print books. And that helped, because yeah, you can imagine writing a book and you see this manuscript on from the Milanese bank going around. It takes time to write it. And if you copy it by hand, you'll probably make mistakes. Yeah, you can add some extra info in the margin and you can even add it to the text, but yeah, it takes time. It takes time, and there's no guarantee that we both have the same copy of that text if we have two hand-copied versions of it. They do look beautiful though. And so for quite some time, people thought that the printing press was not going to make it because people didn't want to have these handwritten books. They are much more beautiful than the printed ones. But the printed ones did become the status. The Arithmetica Practica here is, I don't have the 1544 edition, I do have the 1556 edition, which is probably the oldest book that you'll ever have in your hands. Marvel at it. It's a book that, in Latin, it's about arithmetic, and you'll notice that it has mostly the new Arab numbers in it, as do the 15th century manuscripts that go about. Yeah? So, not much revolted there, not much new there. Yeah. At the left there is this new hand calculating method that never really came off. And on the right there is this copy of the Arithmetica Practica. Yeah. So new prints. I have a few other prints here. These are facsimiles that can 3 times the same booklet. It's about calculating on lines or calculating with the feather. Calculating on lines, I'll show you momentarily. Calculating with the feather is by writing the numbers, by writing them down. So it's 3 times the same booklet, but that's just how you. So the printing press helps with the dissemination of knowledge, mathematical knowledge in particular, but all kinds of knowledge, as you may imagine. One of these knowledges that was spread around was the new horizons that people set sail to. Trade and expansion. I don't like even the word discovery. It supposes that if you discover, the Americas were discovered, was usually the phrase until a couple of decades ago. It kind of supposed that no one was living there. People were living there. It wasn't discovered. Europeans arrived in America and took possession of the whole of the land. But discovering presupposes that no people were there yet. Well, they were. They've all been killed. But that's little detail. Trade and expansion. It affected map making. It affected navigation, but it also exposed political prejudices. Well, map making is described quite elaborately in the syllabus. The idea of map making on sea, if you go in your ship on the sea, you sail off, what you need if you want to be safe is you need to position your ship. What people used to do was stay close to the coast and see what the coastline looked like. Coastal line, they had pictures of these coastal lines, so they could say, oh, we are about here. And they had pictures of the various cities that they could pass, and they could see, oh, well, this looks very like the city that I have pictured. So we are in Spain or in Portugal. That's the way that people went about, like pictures. Looking at pictures of the coastal line. That's how you navigate in the 15th century. Trying to navigate by determining your position on the globe is quite hard. You can do that if you're standing still outside on the square outside. Then it's quite easy. Then you can use the sun and the time. You can figure out what is your geographical position. But if you're on a ship which is dancing a little, just establishing a place where the horizon is already quite hard. Finding out where you are, if you have no point of reference on that horizon, is even more difficult. So if you can see, if you can spot a piece of land which you're fairly certain that it stays in place, that helps. But if you can't, if you're somewhere in the middle of the ocean, that's quite hard. And most navigators were quite awful at it. So we know of Columbus, for example, that that his positions were about 1,000 kilometers off. He made mistakes of about 1,000 kilometers, which is not that bad, perhaps over that distance, but it does bring you from Canada to New York. So map making it affected map making in the sense that it became fashionable, and mind you, fashionable. I use the word fashionable, it's not practical. Remember the story of Columbus? It wasn't practical at all, but it became fashionable to do your measurements mathematically and determine the position on the globe, and thereby your trade route. Navigation became, or was claimed as, a mathematical expertise. It also exposed political prejudices, yes. The people came across nations, states, other people who were in complete different, who lived always in isolation, or who had been in contact with other groups, but not with Europeans. They were confronted with completely different beliefs that they hadn't heard about yet, completely different political systems. It could be convenient to wipe them out immediately, but mostly they didn't, or somehow they didn't. And then the stories about this different political system started growing around. Novels about completely different political systems, where there was no king, were written. These ideas sprang up because of that work a result of the expansion. The new horizons, both literally in coming to places where no man has gone before, no European man has gone, but also metaphorically in the sense that new visions of society were coming out. Map making here, this map of Sicily, you can also spot this, and this is a geometrically accurate map. Making such a map is completely useless unless you want it on your wall as a king of Sicily to show your grandeur. That's what it was made for. That's what it was made for. To show off to others. Look how big we are. We can fill a whole piece of paper. That's more or less the idea here. And how limited this could still be yet. Yes, mathematicians became involved in navigation, in map making, but in fortress building, in walking, in various fashions, but not in every fashion. Here is Simon Stephen. He's described more extensively in the syllabus, and I'll have this booklet handed down. This is one of his books that he wrote to, it's a facsimile as well. It's a late 16th century book that he wrote about adding numbers in the decimal system. Not only ordinary numbers, but also fractions, so decimal fractions in a sense. Yes. One of the things he suggests in his book, or in the preface to his book, is to start counting decimally everything, not just doing arithmetic decimally, but also the number system. Not just the number system decimally, but also the system of coins, of lengths, of surfaces. Not as we do it today, because the metric system that we use today is even more intricate than that, but doing your measurements decimally. This was kind of odd at the time. coins, definitely, they were issued by the king or by the king's exchequer, not by a mere mathematician. Certainly not by Simon Stevin. So the suggestion that he could do this suggestion kind of indicates that he was very, very friendly with the Prince of Orange at the time where he was working for, and he could do the suggestion. But the suggestion was not taken up, was not used in practice, was just left as a suggestion. Yeah, we could do that. Yeah, sure. Who wants to? Every city had its own coin system where in one place the dime would be contained in a nickel worth, every nickel is being worth 6 dimes, and then the other place would be worth 8 nickels, 8 dimes. Yeah, so, and that could vary from, I think, from 4 to 12 within just this small area in Holland, province of Holland. And so the coin systems differed greatly. You had the Leiden coins, you had the Amsterdam coins, you had all different kinds of coin systems. Like we treat our marbles today in the school ground. Stephen could not achieve anything there. That was the area of politics of higher people. But making maps, designing fortresses, he could do that. There he was worth his money. Politically, economically, the world changed from a land economy where land and horses counted. Yeah, how many acres of land, how many horses can you send to the aid of the emperor? That was the question that counted. That was on the basis of which your worth to the world or your worth to the kingdom was counted. And that changed to a monetary economy. The banks. The banks became important. The large merchant houses became important. And they had their view on mathematics. They did like things like algebra. Calculating something that you didn't know, that's cool. That was that thing. That was an extension to common arithmetic that they were used to. And cool in the same way. That was their cup of tea. So from land and horses to the monetary economy, that's the monetary economy. The monetary economy is the place where you wanted to be. Both the papal office and many kings tried to counter that shift. Yeah? They noticed this was happening and they started collecting taxes. The papal office started collecting tents. So every you wanted if you were done, if you had committed sin, you could pay off your debt to God by donating money to the church. Well, you go. Yeah, they noticed that money was becoming more important as the way of economical progress, economical power. But certainly the papal office reacted too late. Counting on the lines, calculating on the lines as a way of calculating disappeared because of influence, incredible influence of these banks and merchant houses that wanted to use these numbers on paper. They had a need of a bookkeeping system. They needed to account for what was going on. The present-day accounting system. So the rules of arithmetic lines disappear slowly in the 15th century already. So we don't have to wait until the scientific revolution for that shift to take place. Here, in the this is from the Magna Philosophica. There's already a shift from calculating on the lines to calculating with ordinary numbers. This page comes after the pages where it is explained how to calculate with ordinary, with our Arabic numbers. So we want to see this because it happens a lot. But that's why he treats this. Theologically, things started shifting around. The pompous man you see here is Emperor Rudolf II, Emperor of the Royal, Emperor of the Holy Roman Empire, yeah, or German nation, of course. So it was Prague. He's not one of the people who got defenestrated, which was one of my favorite forms of execution. Defenestration is what happens with people in Prague, in the vicinity where fortresses are built on large cliffs. And defenestration means simply throwing someone out of the window and plunges down the cliff. That's a remarkable way of it. But anyway, Rudolf II was one of these emperors who got into a lot of trouble trying to appease the papal office on one side. Of course, he was crowned by the Pope, so he had to be friendly with the Pope, and having to cope with all these different Protestant factions coming up. Protestant factions coming up through the printing press, the new beat a good match at that time in the Milanese Horn. Friendly with the Pope, he was a good friend of the Pope, so he could mock the Jesuits who were gaining in importance and power at the time, because yes, it was the Jesuits who were very good at mathematics, who were building the best fortresses of Europe at the time, who could counter these bloody Protestants in the north. It was the Jesuits who would, in the end, also save the papal office. The Jesuit order was the most intellectual and most, military best equipped group that would, in the end, save the papal office. And that's exactly the group that Galileo opposed. And then the Pope died, a new Pope was elected, and that was not his friend, so he got into a lot of trouble. That's the story of Galileo as well. Sad story of picking the wrong battle at the wrong time. And don't go about claiming alternative truths if the world around you is collapsing. That's the motto here. So yes, a lot of Protestant factions, a lot of Catholic factions within the papal office, a lot of monarchs tried to profit from the crumbling papal power. The Pope was losing power. Back to the standard view now. What remains? What remains of that standard view? Well, yes, still, Galileo was standing trial before a Jesuit college, but we've added some layers of significance there, right? So it's not just science versus religion. No, at the time, all these scientists, if you want to call them that way, I wouldn't call them scientists, but if you want to call them scientists, all these people, with the notable exceptions of a few, like Stephen, like Galileo, most of them were religious, were popes, were bishops, were priests. Practically all of them were, with a few exceptions who were working at court. And these courts had something to gain. They stood to gain by blowing discord, by meddling up things in the papal bureaucracy. Yeah. So they sent about now and then someone like who was sent out to Duke of Milan just to meddle up things a little bit, trying to, in that way, with intrigues, trying to gain more power for themselves. A lot of things changed in the 16th century and the USA. A lot of these things were interrelated. There was nothing much mathematical about it. Did anything change in the mathematical world? Well, not really. Not really. But then, just out of curiosity, where did this standard view originate? Well, the first time that this juxtaposition of the church and science is mentioned is in this 1876 book by William Draper, History of the Conflict Between Religion and Science. Late 19th century, mind you. And that's exactly the time, and you will be reading that in the syllabus, I hope, that's exactly the time when mathematicians and other scientists professionalized, when they became a profession, and they started delineating their work from that of the until then, until the late second half of the 19th century, science was a priest's job. Universities were church buildings. Go to Oxford, go to Cambridge, go to wherever. What you see is church. It's not because that's not for nothing. That says something. For next week, have a good look at the assignment. Please reflect on the questions, although because it's the same church specifically. And see you next week. Thank you for your attention.